So this video is just going to be some introductory comments about the function y equals e to the x and its inverse, the ln of x. ln stands for the natural logarithm. We've been working with some logs now, and this is a special log. E to the x has some unique properties that we'll discuss in greater detail as we go through the term. But the number e is a limit as x goes to infinity of 1 plus 1 over x to the x. If I drop the number 1 in, I'd get 2 to the 1, which is 2. And I went to a calculator and dropped the number 20 in just because I wanted to see how quickly it converges to 2.71, which is just like pi, an approximation. Pi, we say 3.14. So I want you familiar with e being 2.71 so we can get a feel for the calculations that we're going to do the remainder of the term. And I just threw a 20 in and the calculator kicked out 2.65. And if I kept getting bigger and bigger and bigger numbers here and here, it's going to approach 2.71. I just wanted to see how quickly it did. I didn't get there. My first guess was a little off. All right, so we've been practicing writing exponential functions. Let me see if I can move this over a little bit. So I'm hoping that you can write this, given where we are in the term now. I hope you would say all of my y values are above 0. The first one is 1 unit. We've been discussing differentials. And the next one is not 1. The next differential is 2.71. And I'm going to make a 0 out of my first x by subtracting 0. That was redundant. And then we plug in a 1, that's the change in x. And if you look at this, there's an awful lot of unnecessary symbols. There's a lot of things that I don't have to write, like most of it. And I'm ending up with 2.71 to the x. And I want us to know that I'm referring to e to the x in that fashion. So this is the graph of e to the x. Now there are some numbers that I've taken off a calculator. And when logarithms came about, a lot of our astronomers, Kepler and whatnot, were able to work with huge numbers. So this was a big deal. We got computers now which are helping us work with even huger numbers. All right, so here's just some values. E to the 0, we just talked about 1. E to the 0.7 is a good estimation for 2. E to the 1.1, 3. In other words, if I do 2.71 to the 1.1 on a calculator, I'm getting real close to 3. All right, and I got tired of just working with 2s and 3s, so I found out that e to the 1.6 is approximately 5. And we're going to learn our rules of logarithms from this table. Now, what's e to the negative 0.7? Well, what's a negative do? We've been studying that for 3 weeks. That gives us a reciprocal relationship. So e to the negative 0.7 is 1/2. So if I take the inverse of this table, the ln of 1/2 is negative 0.7. The ln of 1 is 0. And I'm getting the same information out of the calculation. I'm just saying it differently. So here I'm going from exponent to quantity. Over here, I'm going from quantity to exponent. And as far as I'm concerned, the two that I work with the most in graphing e to the x functions is 1 and 3. Because that's going to make my differentials turn into a 1 to 3 if I pick the right number. And the right number is 1.1 to give me a feel. All right, so how can I then graph an exponential function easily? Well, let's get one. We'll make it fairly, I don't know how complicated we want to make it. So let's just say we have a function here of, how about 5 plus 4e to the x minus 7 over 10. How about we do that? Well, I know it's exponential growth. Okay, so I can see that. Okay, and what numbers do I want to use? I certainly want to use 7 because that gives me 5 plus 4e to the 0, which I know equals 9, e to the 0 being 1. And I would love to pick whatever gets me 1.1. Well, 10 times 1.1 is 11. Plus 7. 18. So if I pick the number 18, I get 5 plus 4e to the 1.1. If I pick the number 18. Is that what I said? Yeah. 18 minus 7 is 11. 11 divided by 10, 1.1. Very nice. So didn't take too long to get those numbers. What makes a 0? What makes a 1.1 out of the argument of the function? And I will always get a 1 to 3 standardized. That doesn't quite look like 3. It should be a little higher, I think. But I get myself a pretty good graph. I'm having trouble deciding if that's a good one or not. Yeah, that's pretty good. All right, so those are your differentials. Now, this differential isn't going to be 1 because I'm multiplying it by 4. So that means that's 4. And that's not going to be 3 because this is 3 times that differential. That's 12. I should be able to get some nice numbers pretty easily. 7 gets me 4. Of course, y equals 5 is the asymptote. Okay, so I hope you can see 9 units coming out of that. So 9 units come out of that when we pick 7 in this case. 7 made to 0. And what made the 1.1? 18. 18. 12 plus 5, 17. Right? And that's what I'm going to do the whole term. Now, some people like 2. Some people like 0.7. I like multiplying by 1.1 better than multiplying by 0.7. Driver's choice. And if you have a hard time with e to the 0 is 1, you can always pick these 2 exponents. All you need is 2 exponents and then two data points and an asymptote, 2 coordinates and an asymptote, and the shape of the graph. Then you can graph e to the x quickly and easily. Now, what's the inverse of this? Well, the inverse of this, let's erase that. And I'll get the inverse here in a second. So this is one of the things we're going to do. Well, the inputs of the inverse are the outputs of the original. Right? So I'm really going from quantity back to exponent, but I'm doing it in terms of x. So pretend you're solving an equation. Like solve this for 17. What would the operations be? Well, I think you'd subtract 5. I think you'd divide by 4. I think you'd do the inverse of e, which is ln. And that's new for you. You know, you've been hearing it for a few days. You're going to have to hear it for more. So it makes more sense. So where was I? Now I'm at the exponential position. You give myself a little more room. So now I've gotten rid of everything here. Division by 10, multiplication by 10, and then add 7. Okay, now if I'm graphing this, I'm probably going to get a base 3 exponential function. I don't know if it's going to go back to e or not, but hopefully you can see the asymptote 5 here. X equals 5. The inverse of 7, 9 is 9, 7. And 5 to 9 is a differential of x equals 4, a horizontal differential, getting me to that point. The next one should be a horizontal of 12, right? Because I'm tripling. This one would be 4/3, then 4/9. I mean, you can see that differential shrinking, 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 the same way that this height is shrinking, shrinking, shrinking. And so x equals 5, right? Numbers need to be bigger than that. And we can start to see the shape of the logarithm. And then if I want this one, I'm picking 17. 17, no, this is fine. 17 minus 5, 12 divided by 4 is 3. And the ln of 3 is 1.1. So I've got a number that's helping me calculate. 1.1 times 10 is 11, plus 7 is 18. Hope I said everything right there. That's the kind of practice we're going to do. Okay, we don't have to do that now. We can do that tomorrow with a lesson set. It's on your lesson sets and it'll be there. And, you know, if you're getting a lot of the problems on the lesson set right now, writing the equation line, finding 3 points, well, start moving quicker. You know, let's go to the middle of the lesson set. Tackle what you need to tackle. You do have to overlearn the material. Right, which means you do periodically have to see it, or like anything else in life, you start to forget. I'm doing a lot of forgetting now. A lot of forgetting. But you try, we'll just do one more, we'll just graph e to the x. And then I got a couple of comments about ln of x over here, and something else we're going to do with the natural log, and we'll be done. So why don't you try graphing y equals 7 plus 9 e to the x over how about 5? All right, so see if you can graph that. You're pausing the video, I'll just keep going. So I'm getting my signature exponential growth 1:3 ratio. Eventually you stop drawing the differentials. My first differential, I'm going to make it 9. My next is going to be 27, so a little higher up probably. All right. Now, y equals 7, I can see that. I can see my asymptote is the constant. And here's my growth. That's where the calculation is changing and it's growing. Every time I put a bigger number in, e to a bigger number gets me a bigger quantity. What do I pick? I want that exponent to equal 0, and I want it to equal 1.1, and I'm going to get this happening. What makes it 0? 0. Okay, 7 plus 9, 16. What makes it 1.1? 5.5. 5.5, and that means I've got e to the 1.1, which is 3, 27 plus 7, 34. I forgot where I was. Yep, a lot of memory issues. All right, so what we're hopefully going to learn this semester is that the ln function is broken up into 2 parts. Broken up into the growth exponents, which are bigger than e to the 0, right? Which would give me 1 to the x. Right? E to the 0 is 1. And so I don't have any growth or any decay. I've got a flat line. If I do 5 plus 3e to the 0x, I got a flat line of y equals 8. Right? There's no growth or decay here. But as soon as I start putting positive values in, we're going up. Okay, we're going to be increasing. And negative values, we're going down. And I hope you can see that if I put a half in, a third, a fifth, I could keep doing that forever and keep getting closer and closer to 0 in exactly the same way that I'm putting bigger numbers in and going to infinity. And that's happening here as well. So if I want to create 2 to the x as a function in base E notation, then I need to know what gets me, e to the what gets me 2. That has to happen. And if I don't know, and I already do know that 0.7 gets me close, then I go to the calculator. So if I wanted to know how to write this function, I would do the ln of 2. I'd get that number off the calculator. I'm approximating it to be 0.7, and I would have the function e to the 0.7x, and these are virtually very similar. It'd take you a long time to zoom out, or, to see divergence. You put these in a graph. Now, what happens if I wanted to write the 8 to the x function? Well, I actually know that one. How about the 11 to the x function? I don't know that one. I'm not going to get a good approximation. So what would I do? I'd do the ln of 11. I'd get it off the calculator. I know it's got to be a little bit bigger than 1.6. Well, that's 5 to the x. So yeah, I'll stop there. I could do some calculations here and get to an approximation, but not necessary for you to follow that right now. But what I hope you hear is the ln 11 is going to give me that off the calculator, and whatever that number is, e to that number raised to the exponent x is an approximation. And this is what's going to allow us to find our rules of logarithms. So I didn't tell you what the ln of 11 was, but I can tell you what the ln of 10 is. And if you want to try to pause the video for a second and try it, go ahead. But you haven't had much experience with it, I don't think. So I'm just going to do it because the first stage of learning is following. So the ln is begging me to write what's in parentheses in E notation. And I know 10 is 2 times 5. And I know 2 is e to the 0.7. And I know 5 is e, approximately e to the 1.6. And I know my rules of logarithms, so I can tell you what the exponential activity is. 2.3. Because you add exponents here. And this is looking for exponential activity on top of e, and if I do that exponential activity, I get e to the 2.3. Well, there's my answer. And we're going to be doing a lot of those problems. And after we do a lot of them and have some success, we're going to break it down and start to look at the rules of logarithms, which is another way of saying the rules of exponents. Because that's an exponent. And the answer to logarithms is the exponential activity, not e to the 2.3, just the exponential activity. So what else did I want to say here? Not much. That gets us started. I think I can maybe show you the inverse of these functions if I can do this properly. All right, so let's make sure I can see. I do believe you are looking at exponential growth with the 1-to-3 ratio. Now, technically, when you're doing an inverse, you're switching the x's and the y's. I'll do that now. There's your inverse. That's what the logarithm looks like. That's what quantity to exponent looks like versus exponent to quantity. Now, if I flip it this way, I do believe you're looking at decay. Okay, I'll switch the x's and the y's. That's another one that we're going to be working with. Okay, now all I'm doing is planting some seeds. Quick introductory discussion, which means we started the conversation here. And how do we get better conversing? We keep talking. And then we hopefully gain some understanding and some facility with the graphing and the calculations that we need to learn. That will take time. My suggestion is a little every day. Every time you do something a little every day, big changes occur over time. All right, so I hope that gets us started. And we'll tackle some of those questions on tomorrow's lesson set. Well, actually, it's the same lesson set. We're doing it for 2 days. So the second half should start to see some e to the x and ln of x problems. We're going to see a whole lot more as we continue, as well as some of the trig that we started. All right, have a good day, everybody.